Hello again to MT3 in vector spaces. In this video, I'd like to show you some more ways of looking at the inner product, of writing it down, of kind of understanding what it is, where we will look at the link between the inner product in its formal form and how it relates to Dirac's notation, and give you a more practical way of computing the inner product. And the other part of this video, I will look at some basic and quite useful inequalities which can be derived from the inner product. Okay, we'll be basing the latter part on Riley, Hobson and Bence 8.1.3, but I will show you a bit of a simpler proof to the Schwatz inequality compared to what's in Riley's book. Okay, so the very first thing is notation. We've been seeing the inner product in the Dirac form, so it's the bra-ket notation where A is in the bra and B is in the ket. And we showed that if you're using an orthonormal basis, then the inner product can be written in this simple form. Sum I goes from 1 to n. N is the dimension of the space. AI star bi, where AI and the bi's are the components of the vectors A and B respectively in this basis. Now what I'd like to show you is that an equivalent form for this is written as follows. It's A dagger B. This is a dagger and not a transpose. It's not a T. So, sorry. This is not equal to the transpose T. Alright. It's the dagger, and the dagger is also called the adjoint. We'll use this extensively when we get to matrices, so you may as well get used to it now. And the adjoint is a transpose plus a complex conjugation. So it has two operations in it. One is the transpose plus the complex conjugation. So what does the adjoint do to a vector? So let's have a look at how we're going to think of vectors now. We can write the vector A with a bar underneath, or we can write it as a ket, as a Dirac ket, or we can write it as a column vector where the A1, A2 and the ANs are the components of A in a particular basis. Now in these two forms of writing the vector A, we don't have a basis, but when we have a basis we can write it as a column vector. Okay, now remember that the components of A in this column vector will depend on which basis set you choose. And if you haven't understood that, then it's a question you should be raising at a tutorial session. So what does the dagger do? Well, the dagger does a transpose. Transpose means if you take a column vector, it becomes a row vector, and a complex conjugation. So the transpose gives us this thing here, where this column vector has become a row vector where each term has been complex conjugated. And this is what is meant by the Dirac bra. So the vector in the bra side is the adjoint or the dagger of the vector in the ket side. So this is the ket and this is the bra. And together they can form the bra-ket notation for the inner product. Okay, so how is this useful? Well, let's see. So now let's take our inner product of A with B. And what I'm going to do now is write it in its bra-ket form. So in its column vector or row vector form. Now this A is in the bra side, so we have to write it like this. A1 star, A2 star, dot dot dot, AN star, and the B is in the ket side, so we have to write it as a column vector. B1, B2, dot dot dot, BN. Let's write that properly. Now they must have the same number of terms in both of these because they belong to the same space. So they both have n terms in these vectors. And now when we want to compute the inner product of A with B, all we need to do is to multiply each term in the row vector with a term in the column vector, as you do normal vector multiplication, or as we shall see later, matrix multiplication. So it's A1 star B1 plus A2 star B2 plus dot 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 plus AN star BN. And that's exactly what we had when we wrote it in terms of the sum. I is 1 to n AI star BI. So why bother with this new notation? It's because, well, there are a few reasons. Two reasons at least. One is that sometimes it's easier to use this notation here, A dagger B. And we'll see examples of when that's the case. Another reason is quite simply that when I'm computing the inner product, I prefer to think about it in this form rather than the sum, because that intuitively then lets me take the first element of A, star it, multiplied by the first element of B, plus the second element of A, star it, multiplied by the second element of B, and so on. Now, this is up to you. I mean, you absolutely need to understand how to get from one form to another form and understand, how to use these efficiently. And this is quite important. Right, so enough of the inner product. Now let's move on to the inequalities. Okay, the first of these inequalities is called the Schwatz inequality. And what it states is that if you have two vectors A and B, then the modulus of the inner product of A with B, remember, the inner product doesn't have to be real. If you're dealing with complex vectors, the inner product could be complex. So we are looking at the modulus of A and of the norm of, the modulus of the inner product of A with B is less than or equal to the norm of A, let's put vectors there, times the norm of B. Oops. Okay. Now, Riley's book has a rather long proof in it. There's a much shorter proof which works as follows. We define a vector C as B minus A, the inner product of A with B times A, divide this last term only, the inner product of A with A. Now, this might look a bit odd, but what this is, if I wrote it all in its Dirac form, I'll use a different color here, is that C is equal to B minus A, and this looks like quite a lot like the Gram-Schmidt expression we had, except that we've got the inner product of A with itself in the denominator, not the square root in there. That's the only difference. Yeah, but let's see what happens here. So now the proof proceeds as follows. We know that if C is a non-zero vector, then its norm has to be greater than 0, and if it's 0 vector, its norm is equal to 0. But no way can the norm, the inner product of C with itself, be less than 0. So we have 0 is less than or equal to the inner product of C with itself. Okay, now let's put in the expression for C. So on the brass side, we've got this whole thing, but in the brass side, sometimes I'm tempted to drop the bars under the vectors and just simplify my life, but I will be a good mathematician and do this properly. All right. And now let's cross multiply. I'm going to skip a few steps because otherwise it's going to take a little too long to get this done. Let's cross multiply. So we will have b with b plus this term with this term, so that will be the modulus of a with b squared divided by the modulus of a with a squared, and then we have a with a, and then we have the cross terms, which will be minus of let's do it properly. So b with this term here, so that will be minus of b, the inner product of b with a, and then this is a complex number, right? I mean that's a scalar, so a with b divided by a with a, and then we have this term multiplied inner product with b. Now this term over here has these two inner products in it. Now these are scalars, and this term is in the bra side, so these scalars need to be complex conjugated when you perform this sum. So we're going to have minus sign, yes, and we take the complex conjugate of these scalars. That will be ab star divided by a star, and let's put the vector signs there, and then we have the inner product of a with b. Okay, now let's see if we can, well, the complex conjugate of a with b is equal to the inner product of b with a, so we just have to flip it around. Oh, and I forgot that. So if we bring all these terms together, we will get 0 is less than or equal to the inner product of c with c, which is equal to, after a lot of simplification, and I'd like you to do this on your own, it's the norm of b squared, which is simply the first term here, and then what we are left with is simply only one term, which will be the norm of the okay, so let's see how we get all these terms in here. These two terms will be equal because the complex conjugate of a with a, the inner product of a with a is simply the inner product of a with a, and the numerators, once you flip these two around to remove the complex conjugation, you get this term here, so we get minus, and these two terms, so they're equal and coming in with minus sign, and they will, and then we have another term here which is the same as these numerically but with a plus sign, so we're left with just one term in here. Okay, so now we're nearly done. Therefore, the modulus of the norm of b squared is greater than or equal to the modulus of the inner product of a with b squared divided by the norm of a squared, and then cross multiplying, because these are positive numbers, you can cross multiply without a change in the sign. Therefore, and then we can take a square root, and once again, because everything has the same sign, the inequality doesn't change direction, since all the terms are positive. We can take the square root to give us, let's put it in its right form, the norm of a times the norm of b is greater than or equal to the modulus of A with B. And that's the Schwatz, oops, that's not what I wanted, the Schwatz inequality. Now, there is another inequality in Riley's book, which is called the Triangle Inequality. I'm just going to outline the proof of this one here because it's quite easy to prove it, and I'd like you to think about filling in the gaps on your own. So it's a triangle inequality. And what this states is for two vectors A and B, the norm of A plus B is less than or equal to the norm of A plus the norm of B. And once again, you will find this quite useful in your quantum modules. And all this really says is that if you've got two vectors A and B, which form two sides of a triangle, then the lengths of A plus the length of B is always greater than or equal to the length of A plus B. That's all it's saying. Now, how does this proof go? Well, I'm going to outline it here, and so it's not the complete proof. For the full proof, please see Riley, Hobson, and Bence, section 8.1.3. All right, so this is the outline. You start off with the norm of A plus B squared, and that's equal to the inner product of A plus B with A plus B, and that's just cross multiply so those are the, and then we have the cross terms, which will be the inner product of A with B plus the inner product of B with A. And now what we're going to do is combine these two terms. Now, one of them is the complex conjugate of the other. And just to remind you, if you've got a complex number Z and you add it to its complex conjugate, then this will be twice the real part. Actually, that's not the way you write it. The real part of Z. Okay, so this, let's put this in parentheses here. So this then is equal to the norm squared of A plus the norm squared of B plus twice the real part of the inner product of A with B. Okay, and now we need one more relation and then we are kind of done. In fact, I seem to be giving you the whole proof over here. The real part of a complex number Z is always less than or equal to the norm of the length of that complex number. And once again, you should be able to see this, because if Z was a real number, then this is an equality. The real part of a real number is a real number, and that's an equality. If Z is a complex number, then you have to add the bit of the complex number along the imaginary axis to the part that's along the real axis, so you get something that's greater than the part along the real axis. And that's all we need now, because that lets us write this as an inequality. Yeah, so now I've replaced the real part of this with its modulus, and that gives me something that's greater than what I started out with. And now I use the Schwatz inequality. Remember, the Schwatz inequality says that the modulus of the inner product of A with B is less than or equal to the norm of A times the norm of B. So I'm going to leave this for you. And so use the Schwartz inequality to show the triangle inequality, which is the norm of A plus B is less than or equal to the norm of A plus the norm of B. Now, having given you these proofs, I have to admit something. We will make no use of these proofs directly in MT3. What you will find is that the proofs are needed for your other modules, in particular quantum mechanics. Nevertheless, this is a fully examinable topic for MT3 because you need to know how to use and manipulate the norms to come up with inequalities like these. Now in 8.1.3 there's yet another inequality given there, Bessel's inequality. Have a look at it and see if you can understand how it's proved. Alright, thanks for watching, and that's it for now.